So where we will discuss mainly the spatial. So first, let's an assistant professor in the Department of Art and Environmental Sciences, Indian Institute of Science Education Research in Bhopal. So in the first session of this talk today, Professor Ajanta Goswami will discuss about the basic image process, the basic of remote sensing. So where we discuss how we can acquire, images, okay, by using satellite or airborne platforms. So here, so once images are acquired, once you have the images, so what to do with those images? So here I will discuss after that what to do with the images and what do I mean by the images. So by definition, so what you see here in my screen, the left panel, I have some colored image. So for instance, though this colored image corresponds to landscape image, so we will not go to some kind of a specific kind of images. So in general, when I say image, it's a general image. It could be remote sensing, which is your reference image, or it could be a simple digital image taken by the camera. So here in the left side, what you see is a colored image of which is being taken by the landscape image. And then if you go further, so this color image is basically composed of 3 different bands, because the human eye can see the visual bands. So for example, blue, green, red, okay? And these color guns we can assign to different wavelength band images to see the images, to make the color composite. This is how we make the color composite. So here, what you see the color which is being shown by the 3 different layers of images, and which is shown in blue gun, green gun, and red gun. Okay. Now, so this is how we create multispectral images. So forget about the multispectral images. Let's start working with one image. So let's say any of the images which is taken in the green band, blue wavelength band, green wavelength band, or red wavelength band. So let's say, for example, I have taken this blue wavelength band, and so now once you see that, okay, so what you have, so these images are basically it is composed of pixels. So by definition, if I have to define images, an image is nothing but a 2-dimensional array of pixels. Okay, it's a 2-dimensional array. You have x direction and you have y direction. Okay, and then it's an array of pixels. So pixel means what? Pixels is these boxes that you see here. So regular array of these pixels. Okay, and that you can see here in different, which is shown here in different shades of gray. As I told you, so and for this, for instance, I'm just considering one band. So the band, in one band, basically what we acquire is the grayscale images, and the intensity of this grayscale depends upon the radiometric resolution of your image data. Okay, so here you have pixels, which is the regular array of you can consider this as a grid, and each pictorial element. Okay, so here what you have is a digital number. So these boxes, what you assign a digital number. So depending upon the property of earth object that you are sensing, and depending upon the in the which wavelength band of electromagnetic spectrum you are acquiring the images, accordingly the DN number is being assigned to each pixels. Okay. Now, so DN number, the range of DN numbers in your image depends upon, as I told you, depends on the radiometric resolution. So for example, if you have 8-bit image, means total sets of gray value will vary from 0 to 255. So 8-bit means 2 to the power 8. So that is 256. Okay, and since we are starting from 0, so we are not starting from 1, we are starting from 0. So the range of intensity value which is stored in my 8-bit image will vary from 0 to 255, where 0 corresponds to object, darker object. Okay, so that will be shown as a black, and that high intensity 255, for example, will be shown as white. And in between these two and numbers from black to white, you will have different shades of gray, and this is called grayscale image. Similarly, if you have 2-bit image, 1-bit image, simply 2 to the power 1, in that case, you will have a binary image. Okay. Now this is very important. So this is what I want you to see. You don't see image in this color form, but you try to perceive these colored images in terms of number. Okay, so in terms of these numbers, so these numbers basically it tells you the reflectance value or emitted value which is being stored in the image in form of digital number. And now we play with these digital numbers in order to process, in order to enhance the information in which we are interested. Okay, and this kind of processing often we do, for example, if you are requiring photographs. Okay, you are taking photo by using your mobile camera. So before uploading it to some kind of social platform, what you do, you try to enhance the information. There are basic processes which is already inbuilt in your mobile camera, and those processing you perform on image to improve the information, to improve the quality of images that you do. Okay, so here we are. So now we have images and then we have digital numbers. So let's say how we can create our own images. So just to give you an example, how we can create our own image. So I have written a program just to explain you so that will help you to understand from digital number to images. So what is the transition from the digital number? So here what I'm doing, I'm creating an array by using of 0, and the size of my array is 500 by 500. So that is basically the number of rows and number of columns, because it's a 2-dimensional array. Okay, so that gives you the number of rows and column, and then you convert this data array into integer value. So this is the simple conversion that we do. And now what I want to do with these numbers, so at the moment I have a matrix, in that 500 by 500 matrix. In that matrix what I have filled 0 values everywhere. So simply if I plot my data array, how it will look like? It will look black because I have just 0 value. So now what I am saying, I want to create an image by using some random number, a random number that I am assigning. So yeah, it's a 2-dimensional, so I am array of pixels, so I have to apply loop twice for row and for column. Okay, and the value I am assigning here in my image is random integer. So random value between 0 to 255. So 0 to 255 tells you what to do with the arithmetic resolution. Okay, so here arithmetic resolution will be 8 because I have chosen 0 to 255. And the value I am assigning is the random value. Okay, so random integer. And once it is done, then again I convert that data into unsigned 8-bit integer to show. Okay, and if I execute this, so what we expect what I'm creating an image. Okay, by using the numbers that I generated randomly between 0 to 255. Okay, so what I have created by using those values, I have created this kind of image. Okay, so this image is what we see, and what we process is on the digital number. So that you please keep in mind. This concept is very important. Okay, now coming to the slide. So depending upon, once you have digital numbers, depending upon what do you want to do, so accordingly we perform operations. For example, if your objective is to enhance the images, your objective is to stretch the contrast, your objective is to equalize the histogram, and so on. So your objective is to filter some values and only keep some kind of values. So it's all about your application, exactly what you want to do. For example, if you want to do the classification, then you want to group certain range of pixel value into one class, you can do. So basically what you are going to do, you are going to perform classification algorithm. You are going to apply clustering algorithms, you are going to apply some kind of stretching, you are going to apply some kind of histogram equalization, and so on. Okay? Now, so this is what I mean by the digital image processing. So you are processing your digital images. So now coming to the filter. Okay, so in this talk I will be mainly discussing about the filters. So filter is one of the important branch of image processing. So this concept of filter is basically is used in the frequency domain. So where our objective is to modify, restrict some frequency information which is there in my image. Okay. So by definition, image filters are designed to remove specific features of an image based on their spatial frequency. So based on the spatial frequency, we allow some kind of filtering so that we allow certain spatial frequency information to pass and certain spatial frequency information to block. Okay? And this spatial frequency information is related to the concept of pitch. Okay, so what do I mean by the spatial frequency? I will come in a minute. So in an image, in a digital image, what you can have high spatial frequency information, or your image can consist of low spatial frequency information. So when we say high spatial frequency in your image, so the region of an image where the picture is graphed. So basically what you have a high frequency in. So if you take a transient, your intensity value changes in a small space. Okay? So such kind of information when you have in your image will have high spatial frequency information. So now you can, if you want to understand, so the image that we created just now by using the random number between 0 to 255. So here if you take a transient, okay, if you take a transient and plot the intensity value as a function of distance, so what you will get many noises. Okay, and these noises are basically the information that we have is called high spatial frequency information. And low frequency information basically the smooth region. So you have in your region the intensity value does not changes much. Okay, so your intensity value you will not observe much change in the intensity value. So such kind of a smooth region consists of low spatial frequency information. Okay. So this is what it is written here. So the smooth region have a variation of tone that is more gradual over several pixels. These regions have a weak spatial frequency. So based on the frequency information in your image, you can have high spatial frequency information and low spatial frequency informations. Now, as I told you, this name filter is borrowed from the frequency domain processing, where filtering means to passing, modifying, or rejecting a specified frequency component of an image. So depending upon what information you want to keep, what information you want to reject, and how you want to modify the information. So this is what basically this process we do by using filtering. So as we have high frequency information in image and the low frequency information in image. So based on this frequency information, we can design our filters, and these filters are called high pass filter and low pass filter. So filters can be defined into two: high pass filter and low pass filter. So high pass filter is designed to remove low frequency information. So this is a kind of filter so that allows only to pass the high frequency information, okay, and remove all the low frequency information that is there in the image. Okay? And such kind of high pass filter is basically used for edge detection or for sharpening images. Okay? And then another kind of filter that we have is the low pass filters. So these low pass filters are designed to remove high frequency informations and passes low frequency informations. Okay? So in low pass filter, all this high frequency information you block and only you allow to pass low frequency information. And as a result, what you have a smoothing effect. Some of you might have worked on the rainfall data or some kind of data where you have one-dimensional data where you have noises. So to remove those noises, what we do, we apply some kind of filtering to smooth so that I can smoothen out the noises. So this is how basically we do when we apply low pass filter in image. This is exactly what we do. So as an effect of low pass filter, when you block the high frequency information and only allow low frequency information to pass, the resulting image is the smoothing image. Okay? Keep this in mind. In low pass filter, smoothing effect; high pass filter, sharpening effect. And this is why high pass filters are used for edge detection and low pass filters are used for smoothing. Now, so the filters is defined. Now, why we need to apply filters? Why we need to study filters? So there are several applications of filters in image processing. So the first one is the image improvement or restoration. So there your objective is to improve the quality of your image. So one application you can have is elimination of disturbance in point and lines, noise suppression, image enhancements, edge detection, and line structures. Okay, so and then pre-processing before spectral classification. So before we go for the spectral classification, we can apply these filters for the pre-processing. So averaging of field units, elimination of local disturbance that you have in your region, in your image, and discover spatial patterns. So this kind of filter is also used for spatial pattern recognition. Okay, so distinguish area, line, point, object through the Windows operation. And what is the Windows operation that we will discuss? So these are the basic applications that we have for filters. So let's try to understand. So here I have picked two images for you. Okay. So the first one is the microwave image, and second one is the optical image, and which is what you see is the colored image. So can you identify the region where you have high frequency information in this image? Or can you identify the region where you have low frequency information, low spatial frequency information? So let's say if you take a transient, you can follow my cursor. So let's say if I draw a line here, okay, and extract the intensity value which is stored in each pixel. So now I plot this intensity value on y-axis and x-axis is the distance. So what kind of profile you will get? Definitely you will not get a smooth profile, you will get a zigzag profile. And that kind of profile tells you you have high frequency information in the image. Now let's take this image where you have entire region is shown here in red. Okay, so if you take a transient and plot intensity or pixel value as a function of distance, so what you will see that your intensity value in that region is not changing very abruptly, but you have a gradual change or you have a smooth change in your region. So that region contains of low frequency information. Okay, so this is what I mean by high frequency information and low frequency information. So anyway, if you have any question, you can stop me in between. I will be happy to answer. Now, so far we have discussed and we have defined filtering. So image filtering can be performed in two different domains. One is the spatial domain, and this is why it is called spatial domain filtering. And another one is called the frequency domain. So frequency domain is nothing but you transform your image from spatial domain to frequency domain by using Fourier transformation, and then you apply filtering, you perform filtering operations, and then again transform frequency domain to spatial domain. Okay? So such kind of filtering is called frequency domain filtering, because you are not doing filtering here, applying filtering in the spatial domain, but you are applying filters in the frequency domain. Whereas the spatial domain means the image itself. So when we apply, when we do not perform any kind of transformation, but we apply filters in the image domain itself. Okay, on image pixel itself, and such kind of processing is called spatial domain filters. Again, in the spatial domain, we can have a linear filter. So in this class, we will not discuss much about the frequency domain, but we will focus only on the spatial domain filters. Okay? In the spatial domain filter, we can have two type of filters. You can have a linear filters or non-linear filters. Okay? So a spatial filter modifies an image by replacing the value of each pixel by a function of the value of pixel and its neighbors. Okay, so here a spatial domain, we modify pixel value in image by using its neighborhood, by using the value, by considering the value of its neighborhood. Okay, and what is neighborhood? I'll let you know in a minute. Now, if the operation performed on image pixel is linear, then the filter is called linear filter, and otherwise it is not. It is non-linear. So this is very basic concept, and I hope that you know the linear and non-linear spatial filters. Now, coming to the linear spatial filter. So a linear spatial filter performs a sum of product operation, okay, between an image F and a filtered kernel W. So image, I have one image. On that image, I use some kind of filter kernel for the processing. Okay. So here, let's say I say my image is F, and the linear filter or the filter that kernel that I'm using is W of some dimension. So this kernel W is also called Windows, template, or mask. Okay, so don't get confused when you see these names: mask, template, Windows, and kernels. All they are same. And what is this kernel? This is basically an array whose size defines the neighborhood operation. So it is your filter or your mask is also, it is an array. So whose size? So depending upon what is the size of your filter, 3 by 3, 5 by 5, 7 by 7. Okay, so that tells you, that defines the neighborhood operation. So how many neighborhood in my image I should consider for my operation. Okay, so that is determined by the dimension of your kernel, and which coefficient determine the nature of filter. Okay, so this dimension of your filter determines the neighborhood operation, how many neighborhoods will be involved in the processing, and the coefficient of each coefficient in my filter determines basically the nature of filter. So what kind of filter I want to apply, whether it's a low pass filter, high pass filter, whether it's an edge detection filter, and so on. Okay. Yeah. So in linear spatial filter, what we do? We apply sum of product operation. What do I mean by that? So now you are familiar with the image that is nothing but a two-dimensional array. So let's say this is my image. On the top, what you see, I have an image matrix. Okay, and here the region that is shown. So this region I will perform just here to explain. Maybe yeah, you can consider the entire image. Okay, just to explain you what I am saying, I am applying window in this region. Okay, which is shown here. The view motion of this region is shown here. Okay, so this F stands for the image, which is my raw image, in which I will apply the filters, and this W represents my kernel. Okay, kernel is, which is the mask window. Okay, and then what I'll do, it is so in the linear spatial filter is nothing but a sum product operation. So by using this image and filters, by what I will do, I'll use the sum of product operation to modify that pixel under consideration. And here in this particular case, the pixel which is under consideration is shown here fxy, which is the center of in this particular image. Okay. So this W is the mask. This is the 0, 0 position. Then you have -1, 0, -1, -1, 0, -1. So this is the row and column. So this means you have, this is your 0 row and this is 0 column. Means the center pixel. You have defined your center pixel, which coordinate is 0, 0. And according to this, with respect to this center pixel, what you have, you assign the position of other pixels. Okay. Now, so to do the sum product operation by using image and window, you can simply write gxy. So gxy is the output image. Okay, so once you apply the sum product operation by using on your image by using the kernel, what you get an output image, and that output image is gxy. So this is simply, it's a multiplication and summation. So you take a product, so W, this pixel W -1, -1, and that will get multiplied with this pixel, which is here, the common pixel, image pixel, into F x -1, y -1, and so on. So this is how we do. And by doing that, the final this pixel under consideration, the value of this pixel will get changed. Okay? So this is the sum of product operation that we apply. Now, we do so because this operation we have to apply over the entire image. So how we do? So each time, so we process the center pixel or pixel under consideration. Once processing is done, we go to the another pixel, we go to the another pixel, we go to the another pixel, and so on. And by this way, we capture entire image, and we modify the value, pixel value of our image. And that process, okay, so that process is called the convolution operation. Okay, so the convolution operation, basically convolution is nothing but the convolving your filter on image, and by step, what we do, we change the pixel, the value of pixel as under consideration. So for the whole image, the convolution filter is defined by shifting the filter kernel pixel by pixel. So for example, in this schematic, what you see, that my pixel under consideration is this center pixel, which is shown here with this white color. Once the processing is done, so this kernel WRS, you move one step further. Okay, now the pixel under consideration will be here, this pixel. Okay, that you see here, where my cursor is located. And again, next step, you go to this position, go to this position, go to this position, and then so on. And by that way, what we do, we process the entire image. Okay, so the equation that we give for the filtering operation, Gxy, which is the filter, f x comma y, which is the input image, and this sign is for the convolution operation, and WRS. So W is the window of some size. Usually, in image processing, we prefer odd size kernel to ensure the symmetry of the filtering process. Okay, so in image processing, usually we select odd size kernel. Okay, just to ensure the symmetry. So when I say odd size kernel, it is 3 by 3, 5 by 5, 7 by 7, 9 by 9, and so on, 11 by 11. So this is how we perform convolution operation on image. Now, if you notice, so let's take an example. So this is the image that I have, 121202, okay, which is shown here with this dark gray. This is my kernel, okay. So this is a 3 by 3 kernel. Size of this kernel is 3 by 3, and whose coefficient is what? Coefficient at different location is what? The center pixel coefficient is 1, and then coefficient is 0, 0, 1, 0, 1, 1, 0, 1. So these values are coefficient, and the size 3 by 3 is the size of your kernel, and that will determine the neighborhood operation that we are going to perform. So if you use this kernel and start processing your input image, so what you will see that you cannot process this pixel, the corner pixel, also this pixel, because you do not have any neighborhood value before and above this pixel. Okay, so in that case, the location at which you have to start is with this location. In case of 3 by 3. Similarly, if your kernel size is 5 by 5, accordingly you have to select other position. So by that way, if you observe, so you are basically using information. Okay, so you are not doing anything with these numbers. If you are applying the convolution operation on your with the given size kernel on your image. So this is one of the biggest problem in image processing. So how to deal with that problem? Okay, so because we don't want to lose any information, and either we want to reduce the size of our image. And as you can see here, if I start doing processing from this point pixel, means in the resulting image, the dimension of my input image will be less as compared to the original raw image. So what we have to do in order to process this corner pixel, we have to do the padding, and that operation is basically we artificially generate some pixels, okay, in our image. Okay, so here in this case we have added one column and one row to just M and in the side of this corner pixel, and similarly we have done here in the right extreme of this pixel. Okay, so we have created one extra row and column and padded with the 0. So such kind of operation is called padding. Okay, so now after the padding, what you can do, you can start processing. You can process with start your processing with this format because you have the pixel here for the neighborhood operation. So this process is called padding. So you can have different types of padding. So the one padding, depending on what values you use for padding, you can have 0 padding, constant padding, you can have nearest neighborhood padding, or you can have reflect padding. So here in this case, we have used 0 padding, and what kind of padding you want to do depends on your understanding and your application. Okay, so for what purpose you are processing your image. So accordingly, you have to select the padding. So the constant padding means you can select any constant value that you think that will not change your change the value of your other pixel. Okay, so in that case you can select any constant value. You can have a reflect, or you can have a nearest neighbor value. So in nearest neighbor, what you can see what is the nearest values. One, you can just duplicate these values. Okay, and similarly you can do with the reflect padding. So these are 4 different kind of padding that is required when you are doing when you are performing filtering operation. Now, so depending on the kernel size, you have to select how much you need to do, how much image you need to pad. Okay. So for example, if your kernel size is n by n, n is the row and n is column, the image is padded with minimum of n minus 1 on 2. So in, let's say 3 by 3 kernel, so in that case 3 minus 1, which is 2 by 2, 1. So in case of 3 by 3, you will pad row and column with 1. If you are using 5 by 5, in that case you have to generate an addition and you have to pad 2 columns and 2 rows. Okay, in either side. So this is all about the padding. Now, so as in the beginning I told you, so you have different filters, low pass filters and high pass filters in the spatial domain. So let's first discuss the spatial filter, which is in the low pass filter. So it is also known as average filter or smoothing filters. So the low pass filter are also known as smoothing filter, or often it is called averaging filter also, depending upon what kind of processing you are doing, are used to reduce the sharp transition in intensity. So here these filters basically we use to reduce the sharp transition. So where we have abrupt changes in the intensity value, so those information we reduce. And it is applied for the noise reduction. So as I told you in the beginning, so the random image that we generated. So what you have is random, in that image what you have is basically the noise. Or you may have image where some random noise is added. And now your objective is to get rid of that random noise or that noise in your image. So for that purpose, what you will do, you will apply low pass filter. So a smoothing is used to reduce irrelevant details in an image, where irrelevant refers to pixel region that are small with respect to the size of your kernel. Okay, so and then convolving is a smooth kernel with an image blurs the image with the degree of blurring being determined by the size of the kernel and the value of its coefficient. So once you perform the convolution operation, okay, so once you apply the low pass filter, so as a result what happens, because you get rid of the high frequency information, so as a result what you do, the resulting image will have blurring effect. Okay, so you will have blurring effect at the edges, and this blurring basically depends upon the size of your kernel. So what is the size of your kernel that you have chosen for convolution, and the coefficient. So what is the coefficient of your kernel? Okay, so the blurring effect is basically depends upon the size of your kernel and the coefficient of your kernel. Let's see. So one of the famous or most widely used low pass filter is also known as the box filter. So whose coefficient is 1. Okay, so this is a 3x3 kernel whose coefficient is 1. Such kind of filter is called box filter. Let's say this is your Lancet. This is a Lancet TM image which is recorded in band 5. In that image, if we apply this box filter, okay, so the resulting image, this is the resulting image GX1. So after applying this box filter, what we expect, so this is a low pass filter, so what we are doing, we are suppressing the high frequency information. Okay, we are just allowing to pass the low frequency information which is there in my image. And then one thing you can notice, which is the coefficient 1.9, which is 1.9, which is called normalizing constant. Okay. And this normalization is very important because in the case where the average value of an area of a constant intensity would equal that intensity in a filter image. For example, if you have a constant image, constant value in your raw image, in that case, if you apply this low pass filter, that constant value will not change once you apply this normalization. And normalizing the kernel in this way prevents introducing the bias during the filter. Okay, so this is why we don't want to have any bias in the result. So this is why we use normalizing constants, which is 1 upon the sum of coefficient. So here the sum of coefficient is 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1 by 9. So if your coefficient value is different, accordingly this normalization constant will change. The denominator of this normalization constant will change. So if it is visible to you, what you can see here after applying this low pass filter, box filter, what happens in the resulting image, it is smooth, as you can observe at the edges. Okay, so this is because of the blurring effect. Okay, so to conclude here, when you apply low pass filter, box filter, okay, or every filter, what happens? You have a blurring effect at the edges. Okay, so every filter blurs the image. Now, can have accordingly, so this is the box filter. So you can decide some weightage. So here in this particular case, we are giving weightage, extra weightage to the central pixel, and then the cell which is nearest to the central pixel is given next weightage, and the least weightage is given to the pixel which is far from the center pixel. So if you calculate the distance from this pixel to this pixel, this pixel to this pixel, this pixel to this pixel, so here distance is larger as compared to this distance, and this is why this corner pixel has been given less weightage. This center pixel has been given maximum weightage, and this neighborhood pixel, close neighborhood pixel is given 2 weightage in this particular case. And this is the normalization factor. So as you can see here, 1 upon 16, which is, you just add up to 2, 8, and 4, 12, and then 4, 16. Similarly here, so we do not give any weightage to the diagonal pixels, and here you can construct. Here you can construct weighted arrays low pass filter. Now, so this is one image. So as we have already discussed, so on top image, this is the raw image, and there what you see, so the information is hidden because of this random errors, because of these errors that you see here, the dotted. And such error is called salt and pepper effect in your image. So these high frequency information, so if we apply low pass filter, so basically we will block the high frequency information, and by that way what we can do, we can suppress these voices in our image. And as a result, what you see that all these voices is being removed from the image, and what you have now is the filtered image, and which is more interpretable now. Okay, and again, please keep in mind. So if you see at the edges what you have a blurring effect. So as you can see here or Edge region, basically you can see what you can see here. You have some edging, smoothing effect. Now, let's see what is happening here. So this is the raw SAR image. Again, you have some high frequency information, and we are doing processing. We are applying low pass filter. So we have used 5x5 mean filter and 7x7 mean filter. Okay, so we have just we have used the same filter, but we have changed the size. Okay, in one case we have used 5x5, and in another case we have 7x7 filters. So as a result, what we observe? So what we can see here, so after applying this mean filter 5x5, so you have blurring effect, and that blurring effect increases as you increase the size of your filter. Okay, size of your mean filter. This means one of the drawback of average filter, okay, is though it reduces the high frequency information, but it suppresses, it smoothes the image, it blurs the image. Okay, so blurring is one of the drawback of applying average filter. So now this is the current ongoing research area. So how we can how to apply, or what kind of filter, low pass filter should we select so that we can avoid the blurring effect. Okay, or we can preserve the edges. As you can see here, edges are blurred. Okay, so now, so let's see what are the edge preserving filters. So what are the filters that we can use? So at the same time we perform the low pass filter, but we also preserve the edges. So one of such kind of filter which is non-linear is the median filter. Okay, so in median filter, what you do basically, let's say you have, this is your raw image. Okay, so this is the DN value of your raw image, and then it's you are applying a 3x3 mask. Okay, in this particular case. So what you do, you order this value from, okay, from 0 to the maximum value in this 3x3 neighborhood image, and then what you do in this neighborhood, you find the median value. So what is the median value? So in this particular case, the median value is what? 58. In this particular case, your median value is what? 153. So now this center pixel where you have 0 value, abrupt black, or here the median value where you have high reflectance value. So based on, by using this median filter, what we have now, this 0 pixel, the center pixel value will be replaced by using this number, this median value, which is 58. And now here this case, this 156 will be replaced by 150. So here you are not having much effect, but here, as you can see here, because of the neighborhood, when we are applying median filter, here the median value is much higher than the value which was originally assigned for this particular case. Okay, so these median filters are basically low pass filter that reduce the high frequency information in your image, but at the same time it preserves the edges. Means it smoothes the image, but at the same time it preserves the edges. So it minimizes the blurring effect. Okay, so like I told you, the median filter serves as an edge preserving smoothing filter. So this median filter is also known as edge preserving smoothing filter. The median filter can remove isolated noise without blurring the image too much. And the median filter can be performed in a vertical or horizontal direction only if the filter window is one line or one column instead of a square. So if you want to perform this median operation in one dimension or two dimension, it's up to you. In column, if you want to do apply in hot direction, column direction, you can select. This is the advantage of using median filter. Now you can have another kind of filter which is called the adaptive mean filter. Am I audible? Can you confirm? Anyone can confirm?
Yes, sir. Yes, sir, you are audible.
Yes.
Yes, sir.
So now let's see the adaptive median filter. Okay, so this is also median filter, but the way we calculate median is this adaptive way. So in first medium we consider these image pixels. Okay, so in first medium consider the center pixel and the diagonal pixel. Then in second medium we consider center pixel and the immediate pixel. And in third medium we consider only the center pixel. Okay. Now let's say you have let's take an example of our previous image. Keep this value in mind: 55, 58, 65, 57, 0, 63, and so on. So same image now image I am taking. So here the first median will be we are considering this diagonal pixels. Yes, what are the diagonal pixels? And by using these diagonal pixel and center pixel, calculate the median, compute the median value. So if you order this, so 0, 54, 55, 65, 68, now the median value is what? 55. So my first median in my image, raw image is what? 55. Now I'll go for this configuration. Okay, where I consider the center pixel and its immediate neighbor. So there I have considered this 8 value 0, 63, 61, 57. Out of these values, what is the median value? So median value is 0, 57, 58, 63, 61, 63. The median value is 58. My first median with this configuration is 55, second median with this configuration is 58, and now the second median, which is the center pixel with this configuration, is 0. Okay, so now this calculate the median of these three medians: median 1, median 2, median 3. So what is that? Here, median 1, median 2, median 3. So this is the 0, 55, 58. Now the median value is 1, 55. So this center pixel, okay, now this center pixel will be replaced by this median, and now that value is what? 55. Okay, so here we will put 55. So this is how we apply the adaptive median filter. Now another kind of median filter is that we use is the k nearest median. So k nearest means that depending upon the number of nearest. So we are not considering the all nearest, but we are considering some number of nearest. Okay, and those nearest neighbor we are using for the to calculate the median. Okay. So for example, here in this first image, we have considered this. We have considered this median. Calculate this median. Median value here. So the median in first image is 0, 54, 55, 57. So this is the median value. And for in second image, you can calculate the median. So accordingly, we have this one. Okay. So in k nearest median, you just consider the nearest. Okay, depending upon how many nearest neighbor you consider, you calculate the median accordingly. You can say 5 nearest median, 3 nearest median. Okay. So this k nearest median filter is more effective for removing noise and preserving edges than the k nearest mean filter. So you can have mean filter also. So for example, in k nearest mean, the mean value will be replaced by set of pixel value will be replaced by 44.8. However, when you consider this median, so the value is much higher. Similarly, in this case, almost the same. So, but instead of using the k mean, if you are using k nearest median filter,
जो हमने एक्सपोर्ट किया था वो एक्सपोर्ट हो गया
this is how we use median filter to perform a smoothing effect at the same time to preserve edges. And then you can have a filter which is also known as filter. So for example, in this image, the center pixel value will be replaced by the majority value. So here if you see what is the majority value in your image, and this 3 by 3 neighborhood is 6. So this center pixel value will be replaced by this 6 value. And then you can have conditional smoothing filter. So conditional smoothing filter means you can program. So let's say in first level of my raw image, I apply this filter, and then the output of my first filter, and that output I take and I apply some other kind of filter. So this kind of filtering, nested filtering, you can generate depending upon your object. And such kind of filtering is called conditional filtering. Conditional filtering means you are doing some kind of nested filtering. So step by step, in one step you apply some filter, second step plus second type of filter, third type of filter, and so on. So this is all about the low pass filter. Low pass filter, where our objective is to smoothen the image, block the high frequency information. Okay. So to smoothen what we have been doing basically, if you take the average, okay, so that will help you to smoothen out your image. Okay, and then we discuss different other types of non-linear filters, which are the median filters and mean filters. Now let's start discussing about the high pass filter, which is also known as the sharpening. Okay, so it's which is also known as edge detection filter or sharpening filter. So it basically enhances the edges that is there in your image. Okay, so sharpening highlights the transition in intensity. So if you have some transition, or if you have some edge transition there, you have when the value changes, that location is the transition. Okay, and which is also known as mathematically called edges. So at edges, high pass filter will highlight those edges. This is why it is also known as edge detection filter. Edges and textures in an image are typical example of high frequency information. And then high pass filter removes low frequency image information and hence enhances the high frequency information such as edges. See, in first case, in low pass filter, it is smoothed. It blocks the high frequency information, whereas high pass filter, it will allow high frequency information to pass and block the low frequency information. And as a result, what happens? It will enhance it, or it will detect the edges. It will enhance the edges in your image. How to enhance edges in digital images? Let's see. So if you see this image, this is a grayscale image, so where you have a region where intensity value changes, you have transit. For example, here, let's take an example of this river. So if you take a transit across this channel, okay, so what you will see a sudden change at the bank of this river, and then the intensity value will be seen, and again when you encounter the bank, again value will change. So such change, okay, this such abrupt change in the intensity value determine the edge. Okay, and we are interested in finding those edges. And for that purpose, what we will do, we will try to identify the location where there is abrupt change. Okay, so as you can see here in this image, there are many edges. So for example, edges means there to intensity value. You see any abrupt change in the intensity value, that can be considered edges. Okay, now, so what is the concept behind high pass filter? So as we saw that image blurring could be accomplished in the spatial domain by pixel averaging or smoothing in the neighborhood. So what we have been doing, so when you take an average, when you apply average filter, so what you are doing, you are smoothing out the image. Okay? And because averaging is analogous to integration, so averaging means you are taking a summation. So that is basically in continuous domain is called integration. So similarly, when you highlight the high frequency information, that is logical to think that can be accomplished by the spatial differentiation. Means when you add the pixel values in your image, the resulting image is what? Smoothen image. So when you take a difference, okay, when you take a difference which is analogous to this differentiation in continuous domain, that will give you, that will highlight, that will give you the edges. So let's take an example. Let's say I have one dimensional grid, some random number. I say 1, 2, 1, 1, 1, 5, then 2, 2, 2. So when you take a difference, okay, so 1 minus 1, 0, 1 minus 1, 0, 5 minus 1, 4. So where you will have edge, where you have high value of intensity or abrupt change in the intensity value or distant number value, that value will be highlighted when you once you take a simple difference. Okay. So most commonly used edge consonant filters are based on the first gradient and second derivative, which is also known as Laplacian. So when you take the first derivative, it's called the gradient filter. Take the second derivative, which is called the Laplacian filter. Okay, so as I told you, integration is smoothing, and differentiation is the basically sampling of your image. So you can, in continuous domain, you can have first order differentiation, second derivative, second order differentiation, and so on. So let's see, we'll see both this first order differentiation and second order differentiation. Okay, so just to understand the concept in case of integration, so integration is applied on the continuous domain, so we cannot apply this in discrete domain, or integration or differentiation. So differentiation is basically different. So you can consider this image as a continuous image. So this here, the real image what we get is kind of this kind of discrete image here. So if you can approximate this image as a continuous image, okay, so in that case we can find the first order derivative and second order derivative. Okay, we are gradient the first order derivative is what? Derivative sum of df on dx, which is the partial because this image function depends on the x-axis and y coordinates. So this first order differentiation, first order partial differentiation in x and y upon del y. Okay. Similarly, if you take another second order differentiation, which is the Laplacian, which is second order derivative in x direction and second order derivative in y direction. If you sum them, what you will get is the Laplacian. Okay. Then this I, j are the unit vector. So now let's apply this in discrete domain. Okay, so what this equation we have written is for the continuous domain, and same thing what we will do, we will apply the discrete domain because our image is a discrete, contains of discrete values. Now let's think about the gradient. Okay, so the spatial gradient is a measure of how abrupt a change is in a given direction. So any direction, if you need in your image, you can move in x direction or y direction. So how your value is changing along a line or along a triangle. Okay, so it is defined as the vector sum of change with respect to x direction and change with respect to y direction taken in the direction of maximum gradient. Okay, so that gives you the slope. So in 2 dimension, you can write the differentiation by using gx, which is the output, f of x, which is the image intensity value, x plus delta x. Why? So we are moving it one step in x direction with respect to delta x, and here we are not moving in x direction, but we are moving in one step in y direction. This is why you have delta y here. So that gives you the first order differentiation in x direction and first order differentiation in y direction. So now let's try to understand this concept in 1 dimension. So in one, as I told you, in 2 dimension is nothing but you have your value is varying in x direction as well as y direction. In 1 dimension, your value is varying only in x direction. So let's say I have some number. So let's say I have some, let's say 6, 6, 6, 6, 5, 4, 3, 2, 1, 1, 1, 6, 6. This is the number. Okay, this is a 1 dimensional number. Now, what you do, you plot the intensity value. You create a profile. So where x-axis is what? X-axis is your distance. So let's say if the pixel size is 1, so delta x is 1, which is constant 1, 2, 3, and so on. Okay? And this is the intensity value that we are going to plot. So let's say at first position, what is the intensity value? 6. Second, 6. Third, 6. Fourth, 6. Now, fifth. In fifth position, it has started to change. So now the value will go down. 4, 3, 2, 1. Okay, so this is called the ramp where your value changes gradually. And then you have a constant value 0, 0, is 1, 1, 1, 1. And then you have a sudden change, abrupt change, and this kind of change is called step. So the value changes from 1 to 6. Okay, so this change is called step. and then again you have a constant value. So this is the condition, this is the signal that I have in one dimension. Similarly, you can have in two dimensions. Okay, just to make you understand, we have considered this one dimension case. Now, if you have to think without using using any logic or any concept, if just you have to think that okay, where are the edges I have? So one way of doing this, you can say that okay, if I can take the difference, so where my difference is high, that corresponds to edge, and where I have less difference, that is a kind of ramp. Okay, so to find this edge, the very first thing what we can do is we can take a difference. Now let's take a first derivative. Okay, so dy by dx in this particular case. So if intensity is I, so di upon dx, and this is, so you take a simple first derivative, which is the x value minus x plus delta x. Okay, so this value minus this value, and so on. So by that way you process. So when you take a first derivative, so what happens? Initially you get a zero value, and then you have this change. 6. Okay, 6 minus 5. 5 minus 6. Okay, then minus 1, 4 minus 5. This thing, minus 1, and so on. So where you have same value, difference is what? 0. When the location where you have your value starts to change, what you have some difference. That difference is basically depends upon the magnitude of your change. Okay, so let's say here I have a negative change. So this is why I have negative values here, and then the constant value 0, and then I have a positive increase. And this C, it's because of this magnitude is very high. Okay, and here the difference is what? 5. So by taking first derivative, will highlight the edges. Okay. So if you take first derivative, is what the first derivative 0 at the constant value. So wherever you have 0 constant value, your first derivative will be 0, because the rate of change is what? In constant value, you do not have any rate of change. di upon dx, which is the slope. Okay. Must be non-zero at the onset of ramp or state. So onset of ramp, so this is the onset of ramp. So here you have non-zero value, or here also you have non-zero value. Okay? Must be zero along the intensity, must be non-zero along the intensity ramp. So this is the intensity ramp. Okay, so here because though the magnitude of change is not very high, but it is changing. So the value here on this ramp will be non-zero because the slope is changing. Okay. Now, if you take, so that we will discuss later on, but here just because we are understanding first derivative and second derivative. So similar way, let's discuss the second derivative. So second derivative is what? We are taking again the first derivative, the slope of slope. So dy by first derivative gives you the slope, and when you take a second derivative, that gives you the slope of slope. So where slope is 0, what we will have? 0 value. The constant slope, you will have 0 value. So let's say here 0, 0, and then you have change. Okay, that change is reflected here with -1, and now here you have all this constant value. So 0 to -1, you have changed. So that is captured here, and then again you have all constant value. So the constant value, because slope is not changing, slope is constant. My first derivative is constant, so my second derivative, which is the slope of slope, will be 0. Okay, and in a similar way you can do. You can calculate the second difference. And where you have a state, okay, where you have a sudden change, as you can see here, you can try to observe this value. So after, in this state, you have a high jump, okay, and that state is basically marked by the change in high magnitude value, this value, 5 minus 5, and then you have constant value 0, 0, okay. So where you have state like change, where the magnitude is high, so that is clearly highlighted in your second derivative image. Okay. Now, so in discrete domain, first derivative is nothing but taking a difference. And how you want to take a difference, the forward to direction or backward different, it's up to you, and accordingly you are going to create your filter. So let's say, so this is a private filter, which is first order first difference filter, which is also known as the gradient filter. So here, this is the center pixel value, okay, and then what you are doing, you are subtracting. So this is in the horizontal direction, so you have taken -1 value and you have given +1 value. So when you apply, what you will do basically, you are calculating the difference. Okay, so this is the horizontal. This will highlight the edges in the horizontal direction, and this is the vertical difference, because I told you image is not just one dimension, because here in this case we were dealing with the one dimension data. But image is of two dimensions, you have horizontal and vertical, X and Y. So you have to create two filters, okay, for one for the horizontal direction and one for the vertical direction. And accordingly, you can flip these values depending on how you want to take a difference. You can say instead of -1, you can write +1, and instead of this +1, you can write -1. And similarly, top things can be flipped to the bottom, and bottom things can be flipped to the top. That will give you how you want to take a difference, okay, forward difference or backward difference. And accordingly, because edges, you have some direction, because edges, you can have a horizontal direction edges, you can have a vertical direction edges, you can have edges in some diagonal direction, okay, you can have orientation in any other direction. So if you are doing geological study, if you are doing some kind of civil engineering, where your objective is to calculate or to identify the edges in some particular direction. So in that case, you can design your filter accordingly. Okay. So these are the coefficient of your 3x3 prefix filter. Okay. And when the coefficient is changed, so another guy, so he proposed a high pass filter, gradient filter with these coefficients. So again, he kept the same 0, the center for the horizontal, and then he has given some weightage the center. Okay. Similarly, vertical. So as you can see here, in case of private, all the coefficients were top and in the bottom were 1. But here, what you can see here, the top is -1. Here, this value is -2, which is in case of private -1. Similarly, here. Okay, and these are the diagonal. So once you have this horizontal, vertical, diagonal direction, you can calculate the magnitude. Okay, magnitude of change. So that is basically the gradient in x direction and gradient in y direction. So you take a square root, that will give you the magnitude. And if you want to calculate the orientation, you can simply calculate by arctan gy upon gx. The ratio of your gradient in y direction. So these are the two famous filters of high pass filter, which is based on the first difference, okay, also known as the gradient filter, private and so on. Now let's apply see the example. So here you have an example. This is the raw image in which we have applied Sober filter. Okay, so this is your vertical filter. So when you apply the GH, which enhances the vertical edges. And here, as you can see here, all these vertical edges are highlighted. And here in GY, which highlighted the horizontal edges. So as you can see here, the edges which is in the horizontal directions are highlighted. Okay. Now let's take one real example. So this is the image I like because it was captured. I have taken this image from the Google app. It was captured on 26th of January. I think 2000 or 2019. So that time, I think the fighter jet in the morning was flying, and this is our ISSER Bhopal campus. So yeah, that particular time, this fighter jet was captured by the satellite. So as you can see here, it gives, because if you see the plumes, it has some direction, you have road, you have some direction, and so on. So this is kind of important image in order if you want to understand the filters in different directions. For example, if your objective is to extract linear information from in any of the direction. So we have used this and input image, and calculated the horizontal, vertical, and the direction by using different kernels, Sobel kernels. Okay, so this is the horizontal. So as you can see here, it highlights all this horizontal information. This is the vertical, so all these vertical information edges is being highlighted here in this particular case. And this is the direction. So the way I have designed my filter is that highlights areas in northeast and southwest direction, and similarly northwest and southeast direction. So it's depending on you. You can accordingly construct your own filter. Now, if you this is just the first difference by using Sobel in horizontal, vertical, and diagonal direction. And now, if you take the magnitude of change, so there is the changes in age. Okay, so we have calculated the magnitude, which is simply the gradient, square root of gradient in x direction, gradient square in x direction plus gradient square in y direction. And this is the final image. Okay, so here in the image, so you can apply in this particular image, you can apply some other kind of thresholding also. So if you don't want to very small patches, you can get it. Okay, so now with this image, you can start playing with what you want to keep and what you don't want to keep. So you simply, it's a matter of programming, and then you can retrieve the information which you want. So as you can see here, this plume is clearly captured here. This shape of this slide is captured. All the buildings are captured. Playgrounds, ground is captured. Okay, so this kind of image processing of filtering operation is very important in order to extract information. And sometimes for quick assessment, we use such kind of processing for defense purpose also. If our objective is to, and if you, for example, if you have some kind of very short duration temporal images taken in minutes or seconds interval, in that case, you can calculate the speed at which this fighter jet is flying, or the speed of the any vehicle or any kind of transportation thing is moving in your area. So this is all about the first difference. Now let's see second. So we have already discussed. So in Laplacian filter is basically the sum of your second order difference in x direction and second order difference in y direction. Okay. So in second derivative, 0 in area of constant intensity. So where you have constant intensity value, the second derivative will be 0. Must be non-zero at the onset of ramp and end of the intensity. So where you have edge, so at the edge, you must have non-zero value. Okay, and depending upon what is the magnitude of your edge, you will have Laplacian value, and must be zero along intensity ramp. So here, as I have already discussed in this ramp, because slope is constant. Okay, as you can, first derivative is constant, so second derivative will be 0. Okay, because that value is not changing. So now let's come back, so we can again calculate the second derivative difference in x direction and y direction. So if you just double differentiate the first difference, the value, if you differentiate first difference again, you will get these values. And to get the Laplacian, what you have to do, difference, second order difference in x direction and plus second order difference in y directions. And accordingly, what you will get is this equation, okay, which is shown here. So based on the coefficient of this equation, we can construct kernel or filters. So for example, this is the xy is the center pixel value. This is the center of my kernel, as I have already discussed in the beginning. So that has a coefficient minus. Okay, so this is the center pixel fxy. What is the coefficient? This 4. And then what you have, the coefficient to all other. So x minus 1 y. Okay, so x minus 1 y, this 1. X plus 1 y. So this is x plus 1, this is y. Okay, and then fx, this is fx y minus 1, so this position, and fx y plus 1, this position. Okay, and so according to the coefficient of this equation, we have constructed this kernel, and then the diagonal cells is kept 0. Okay, so this is a Laplacian filter. Similarly, you can, depending upon, so you can change the value. So this center pixel negative value to the positive, and depending upon which kind of difference you are taking a forward difference or say backward difference accordingly. So this value will change. So let's say if you revert that, so the center pixel will have positive value, and then all this immediate neighbor will have negative value. So this is the Laplacian filter of other time. Right. If you can have some extra weightage, you can give some weightage to the equal weightage to the diagonal also. In that case, accordingly you have to increase the weightage for your center pixel. Okay, so all these diagonal pixels will have one value, and then the center pixel is great. So this is the Laplacian. So one of the example of Laplacian filter, as you can see here. So this is the, let's say, this is your raw black and white image in which Laplacian filter is applied. So wherever you have edges, so for example, those edges are highlighted here, and all the regions where you have a low frequency information. Okay, so for example, in this particular case, because the intensity value is not changing. Okay, so these are the low frequency information that is suppressed. And what I have only the edges here. Okay, so this is the result of Laplacian. Another, this is satellite image for which Laplacian is applied. So if the center pixel in the Laplacian kernel is higher than those of its neighboring pixel, the Laplacian is positive, indicating a convexes. So now the way you construct this kernel. So if your center pixel of your Laplacian kernel is higher than your surrounding neighboring pixel, so the Laplacian is positive, indicating convex edge. So when your center pixel value is higher than the surrounding pixel, you will get is convex edge. When the center pixel value of Laplacian kernel is lower than those of its neighborhood, in that case you will get concave edge. Okay? So similarly, in this case, you will get convex edge, and here you will get concave. Okay, so depending upon what is the value of center pixel, that will determine the shape of your edge. Either you will have concave or convex. Now, so again, you can have another kind of edge sharpening filter. So where you give extra weightage to your center pixel. By increasing the weight of your center pixel in the Laplacian filter, you can create edge sharpening filter. So for example, here we have assigned a very high value to the center pixel as compared to the neighborhood pixel, and similarly here in this particular case. So in these examples, what it will give some weightage, and by using that weightage, you can accordingly enhance your images which is there in the image. So now just to conclude here, so what we studied. So edges in digital images for high pass filter, basically the edges in digital image are often ramp-like transition, in which case the first derivative of image would result in thick edges. Try to understand this, because if you have